Hello guys, we got a problem today from David Griffiths. I've written it down over here. We're just going to zoom right into it. Problem 3.3 by Griffiths. Show that if inner product of H and Q acting on H is equal to inner product of Q acting on H first and then H for all H in Hilbert space, then the same thing can be said about the inner product of F and then Q acting on G, and first Q acting on F, then G. I don't know exactly how to word this thing. My vocabulary isn't expert enough, but we're going to try to prove this here. We got a hint from Mr. Griffith. He says, first let H equal F plus G, then let H equal F plus I, imaginary number G. And here I have something that's going to be very helpful. It's literally an equation from chapter 3, which I have not really talked about too much, but this is important here. It says the expectation value of an operator Q is defined as, this is seen in the first and second chapters, the complex conjugate of the probability distribution, which is in our case the wave function psi, the operator sandwiched in the middle. The operator is acting over here on just the regular probability distribution psi, no complex conjugate, integrate over all space. Another way of writing this in this new Dirac notation, which we see several times over here, is this. So this inner product is basically this integral here with the psi star psi dx. That is this little inner product thing and the psi's, right? This psi over here has the complex conjugate on it. You can tell that because it is chilling in one of these things, which is called a bra. The other one is chilling in the ket. And this operator here is acting on this psi. All right, what are we going to do here? We're literally just going to apply this onto this and see if we get this out of it. Then we're going to say proved, and then we're going to say this. Cool. Let's start the proof off. I guess we're going to let's go with a nice little salmon color right here. Okay. We're going to start off with H, operator H. Operators normally have this hat on them. I'm not really going to write that. Let's expand using this first thing. So we have F plus G, and then Q acting on, I'm going to put brackets, F plus G. Looks good. How can we expand this? Well, this is why I wrote this little integral thing, because we have an integral all over here, and inside the integral we have this summation. If you have a summation inside the integral, you can distribute everything, split it apart, and then an integral of a summation becomes a summation of the integrals, because the integral is a linear operator. I don't know if that made sense too much, but basically you can expand this as follows. Well, let's expand the other side first. F plus G. Then here we have Q acting on F plus Q acting on G. That is a bit easier to expand, right? Now here what I'm arguing is we can do F plus G times QF plus QG, distribute all of that. So here we have F multiplied here and multiplied here, and then we have G multiplied here, multiplied here. So we have 4 terms. This becomes F, Q, F. The order matters here. And then we have a plus F, Q, G. Then we have a G plus G, Q, F, and plus G, Q, G. Nice, you see that? So this thing multiplied here gets us this first term. This thing multiplied here gets us this last term. This thing multiplied here gets us this middle term, and then this thing here gets us this middle term. What I'm arguing is that this distribution that happens inside the integral over here, which can be seen here and here, can just be expanded, and you'll have several of these integrals. So you'll have several of these inner product bracket notations. If that didn't make sense, no stress. We're just going to write it down right here. So the first one, we have F and Q acting on F, right? Then we have F and Q acting on G. And then we have G and Q acting on F. And here we have G and Q acting on G. All right. If this didn't make sense to you, literally check this out right here. Write it down like it is literally written down like this. Expand it like this, right? So you have an operator in here. Here you have an F plus G, and here you have a QF QG. It's literally two things being multiplied inside an integral. Expand it, you're gonna get this, and then there's a plus sign everywhere, so you could just distribute this little integral sign, distribute this, and then you can use this exact little definition here to get a bunch of these things here. So I'm just skipping all of that, and I'm going from this step all the way to this step here. And what can we say about this? Whew. I don't know. I don't know what we can say about that. But basically what I've done is taken this, which is given in our problem, apply the hint, and I got this large chunk of stuff. Now I'm just going to take this, apply the same thing, and see if I get this same thing. If I get this same thing, then this thing here is proven. Well, maybe not. Maybe not. We'll see. Let's do it in a different color though. So now we have Q acting on F, and then, or Q acting on H, right? And then H. Nice. Let's expand this the same way. So we have Q acting on F plus G, and then F plus G. Distribute the Q. Sure, let's do that over here. QF plus QG, F plus G. We get the same kind of distribution, but remember the order matters. The order matters here, huh? So we have to make sure to keep the F's and G's on the right side. So notice how here we had the Q's left over only on the ket side, right? That's because we started with this Q acting on the ket side. When I say ket, I'm talking about this thing. When I say bra, I'm talking about this thing. So here, the Q is actually in the bra. So we have Q in the bra here, Q in the bra here. So our final thing is going to have, it's going to look a little different. The Q's are going to be on the opposite side. They're going to be right here. Okay. Let's peep if that makes sense. So we could do the same sort of distribution, and we get QF F plus, let's do the other one, QF G plus QGF plus QGG, right? And that looks good. This one applied with this gets us this, right? And this is in the ket, and then this F is in the bra, so it is left in the bra. And the same thing applies. This one and this one gets us this. This one and this one gets us this. And this one and this one gets us that. Fantastic. So now can we say anything? Well, we have to equate these two, right? Because what I've been doing so far is taking this equation here and applying this to it. This side equals this side. So basically we have this thing here equals this thing here. Okay. In that case, let me just write it down as is. FQF plus FQG plus GQF plus GQG. Okay. Now the cool thing is, we have this other property in the book. I'm gonna throw it up right here, which says that if this operator is hermitian, you're allowed moving it. So if it's here, you can move it here and get it here if it is a hermitian operator. Is it a hermitian operator? We don't know. Forgot a little hat here. But you know what? We're going to say it is a hermitian operator, and we're going to move on to the next line. If it is a hermitian operator, then this bottom line right here, this line, I can move this Q over to this F, and I can move this Q here over to this G. Okay. So I'm gonna write this line in blue. QF, I'm writing kind of small because we're gonna have quite a lot of things here. QFF plus QFG plus QGF plus QGG equals. Now I'm going to apply this change here. QFF. Right. Plus, I'm going to keep it the same here. So here's my confusion. I feel like I can move it here because the functions are the same. So it's literally applying this rule, right? This rule here. This H, we could just change for an F, it doesn't matter. And it says, show that if this is true, so this is taken to be true. But notice here, the letters are different. So I'm trying to show this. I can't move this Q to the other side because I don't know if this is true or not. I'm trying to show that it's true. But if this is true, then I have no problem applying that rule on the ones with the same letters. So this F, QF, I have no problem moving this Q over here. And same with the G. But when we have this F and G combination here, we have an F on one side, we have a G on the other. I feel weird moving the Q here because I'm trying to show this. I can't do it yet because it hasn't been proven. You see what I'm saying? So I've made this move, but then for the other ones, I'm going to keep it the same. So here we have an F, Q, G, and then man, I'm running out of room. But it's okay, next line we're going to cancel some shit, so it's going to cancel out and save some room. So here we have a G, Q, F, and then here I can make this change. So we have a Q, G, G. So basically this thing I've changed over here, this thing I've changed over here. These two things I've kept the same, they are here, right? I just continued here. And then this whole first line I've kept exactly the same here. Now peep this. Here we have a QFF. On the other side we have a QFF. So I can say these can be canceled out, subtract on both sides. Here I have a QGG, QGG, cancel those out. So what are we left with? We're left with this term, this term, this term, and this term. Let's write those out. QFG, how much time are we? 13 minutes. I'm not going to do the other case, guys. Plus QGF equals, on the other side, we have F QG plus G QF. What can we say about this? What can we say about this? Okay, I think we're pretty much done here. Because check this out. What we're trying to prove is that, check the problem again. Show that if this, for all H, is true in Hilbert space. So we've literally accepted this to be fact. The reason how we've accepted it to be fact is we've used it here, right? We've applied the hint. And then we've just proceeded with regular algebra, so nothing's broken, right? Using algebra, we're chilling. Then we got to the stage where we see something like this, and we're like, okay, if we take this to be true, then we are allowed moving this Q because they're equal. You can move the Q here, you can move the Q back. If these H's are the same, this is a general property, it's saying it's true. What we're trying to prove is this more broad proof, which is saying it doesn't even matter if the functions are different. You can still move this Q around and you're chilling. So we're trying to show this. So basically, using the first thing that we took to be true, I canceled out these like terms, these ones here, and I am left with this over here. So what can we say about this? Or we're trying to prove something. Check it out. If I call this first term A and this second term B, and this next one A star, actually star looks like complex conjugate. Let's call this one A dash at the bottom here, and this one B dash. If we show that these are equal, then this equation is solid. And check out what it means if we show that these are equal. Let's check the A and A dash equation. What this equation is saying is QFG is equal to FQG, which is what we're trying to prove, right? Check this. We have two different functions, f and g, and we're taking the operator from one side and we're sliding it over to the other side. This is one thing we're trying to prove. If this is true, then this and this are the same. And the same thing here, except the g and f are switched. On this case, we have g and f like this, or f and g. On this case, we have g and f here. So this b equation, to write in the salmon, b and b minus equation, is basically saying the other case. If q is acting on g and then f, then we have g and q acting on f. So we have both cases. And if this equation is true, then this has to be true, all right? And if this is true, how do we get to this? We literally got to this by imposing this and using this. Fantastic. So, okay, I'm gonna leave this one here for homework for you guys. The only thing I wanna say about this is there's an I over here. Keep in mind that when you have something in the bra, this I, this bra literally represents this right here. So this bra is literally the integral and the complex conjugate. And then this ket over here is just this guy, and this operator is this operator in the middle. So the only difference you're going to have here with this is you're going to have to complex conjugate whatever is in the bra if it has an I. So any scenario where the G right here is in the bra, there's going to be an I. And if you want to move this I around or you want to pull it out or something, this I is going to have a complex conjugate on it. And a complex conjugate of I is negative I. So that's the only thing you have to keep in mind if you want to do this case. But the same thing is going to happen. You're going to get some equation where this is forced to be true. So I hope this was helpful. Doing some kind of hermitian operator, Dirac notation, inner product, bracket, mathematics. Basically, all you need to know is that you can move the operator around. Learn about hermitian operators, learn about complex conjugates, learn about this thing and how this thing is just an integral which you've been practicing with in the previous chapter, and you should be chilling. Thank you guys for watching. I'll see you guys in the next video.